first item on the agenda this evening is a presentation on the Sustainable Renewable Energy Utility Systems, otherwise known as SEREUS. And the lead presenter this evening will be Don Thomason. He's in charge of business development for SEREUS. Take it away, gentlemen.
Thank you, Mayor, and also Betty. Thank you for putting us on the agenda tonight. We're very excited and we appreciate it. It's been a delight working with you. I can't believe it's been over a year since I came to Toledo to meet with you, Mayor, and others. And we really appreciate your passion and how effective you have been in terms of helping us to understand the issues for both the city of Toledo as well as for other cities. So in the way of a brief background, as I mentioned, I am born and raised in Oregon, graduated from the U of O. Thank you very much. And in 1992, my employer at the time moved me to Salt Lake City. And so I've been here ever since. With me are the co-founders of SEREUS, Johnny Krasik and Paul Freeman. They will be taking you through the specifics of the technology and the actual demonstration. I just have to tell you that I've been fortunate to be a part of some pretty exciting and disruptive technologies throughout my career, but they really pale in comparison to the innovative technology Johnny and Paul have developed and patented that will benefit Mother Earth as well as humankind. Before I turn over the slides or turning the time over to them, I thought I would just take you through a couple of slides. By the way, if during the presentation, any of you have questions, certainly write those down so that we can address those during the Q&A portion of the meeting. So the first slide.
Can you enable us to present?
Oh yeah, thank you.
You should be able to. You would just have to share your screen.
Yep. There we go. Okay, everybody can see that okay?
Yes.
Mm-hmm.
Let's go to that first slide, second slide, just to make sure that we're all on the same page. These are pretty fascinating statistics, and I overheard somebody talking about statistics, but these are the best that we could find in terms of some of the issues that you're dealing with. But this is at the global level. As you can see with sanitary sewer, trillions of gallons produced per day. Only a quarter of that is treated and the rest is dumped. And I know those are some of your concerns. At clean water, humans use 3 trillion gallons of water per day. There are shortfalls in nearly every region and country due to climate change. The next global pain is energy. It costs the world $84 trillion per day for energy. 65% of that comes from toxic emitters, coal and gas. And then the last one is trash remediation. Globally, 3.5 million tons of paper and plastic trash is produced per day. And if you were to visually kind of come to grips with that, that's almost 3,000 acres, 9 feet deep of trash. That's pretty significant per day. When we take it from the macro to the micro, for the city of Toledo, we are so delighted to work with the city of Toledo because of your emphasis and your desire to lead the way in green technologies. And as we took copious notes and learned from you, we learned that the priorities are finding an innovative, environmentally friendly and cost-effective waste treatment solution, the ability to eliminate land application of biosolids, reducing greenhouse gases, and eliminate dumping toxic waste streams into the waterways. And last but not least is to create jobs. As it relates to SEREUS's mission, a lot of people put that on the board in their offices, never to be read again. But coming to SEREUS after a lot of this technology was developed, I've just been so impressed with Johnny and Paul's DNA makeup. They truly are about this mission statement. They love the earth. They want to treat it fairly. We feel as though we're stewards of this good earth. And the technology that is being developed stays true to their desire and their vision for helping in that effort. So SEREUS's sustainable and renewable technology produces new and reusable ultra clean water and green energy from sewage, biofuels, oil well production water, and gas. SEREUS units are maintenance friendly, offer low operating costs, and provides the highest environmental alternative for using water and generating power. So that's pretty significant. And, you know, when you look at all the other alternatives or options that are out there, we think that what we have is pretty special. And with that, I'll turn it the next slides over to Paul Freeman, who will take you through what we actually do.
Okay, so when we look at what SEREUS is actually doing, a lot of it is based upon years and years of work that Johnny and I have done, both as consulting engineers, as well as on projects that we have worked on personally. And we have learned that we can use water in an amazing way. So when you take water and you raise the temperature up on it and you keep the pressure up on it, it becomes very oxidative and it wants to be aggressive in tearing things apart. So we can take long chain hydrocarbons, which is basically the makeup of a lot of our waste, whether that's sewage or oil or biofuels, any of those types of things. And we can, on the molecular level, break it apart into its elemental forms and then recombine it into new water, as well as we take all these long chain hydrocarbons out, clean the water that's there. And so we provide ultra clean water and power, and we can do it in a very efficient way. Down on the bottom right is a list of some of the waste fuels that we could use, ranging anywhere from sewage to methane, plant matter, and you can read that. But anything basically that has BTU value or energy value in it, we can break down to that elemental level and clean. So one of the things that is really, really concerning to people is what happens with carbon dioxide, with methane. SEREUS and what it does can provide carbon offsets and sequestration of CO2 and even mitigating methane by eliminating it before it's even created. We could certainly use it in the system, but if we can use that plant matter, if we can use that sewage waste, if we can use those things before they start to break down, then we won't even be creating the methane. As far as CO2 is concerned, a lot of people are really concerned about it, that it is being created. And what we can do with that is we have partners and companies that we've worked with. One is called Solid Carbon Products, and the other one is Exeon Energy. Both of them do very different things with CO2, but both of them take and convert waste CO2 to something that's usable. Solid Carbon Products in the form of carbon black, which is a feedstock for tires, lithium, batteries, carbon fiber, which is a great building product, as well as Exeon Energy. They take that and they make biofuels out of it. And so we can not only create carbon offsets, but we can totally eliminate that CO2 with the partnering of some of those companies that definitely do that. Johnny?
Okay. So the question is, how does it work? What goes in? What comes out? In the typical SEREUS unit, it is built in a shipping container format, and we're able to take shredded screened garbage in as one feedstock, sewer water, sewer sludge, sewer gas, post-processed sewer sludge. those are the inputs that come in, and then as outputs coming out, we end up with electricity. The typical unit is 200 kilowatts to 250 kilowatts. But also we have the water that comes back out that we pulled out of the garbage, or we've made new water. We're looking at about 30,000 gallons a day of RO grade clean drinking water. That could be used for irrigation. It could be put into a culinary system. It could be used even just to return to the rivers without carrying any pollution. We also have gallons of totally distilled water. We also are able to capture out the salts and minerals that were in the garbage, which now there's no toxic or long chain hydrocarbons left, but we end up with some salts, we end up with some phosphorus, we end up with some calcium, magnesium is what I'm trying to say. And these things that were in the plants originally come back to us as minerals or salts. So that's pretty interesting. I'd like to look at this next slide. You know, people ask, well, how much energy really is there in sewage sludge? But sewage sludge has about 64,000 BTUs per pound. That's if it's dried and incinerated. We don't have to dry it, but we can still get that energy out of it. But that 64,000 BTUs per pound means it has about it has about equivalent to a third of the energy in diesel. So per pound, I mean, there's actually a lot of energy there. And so I just think that's a really interesting factor. And using that as energy to make electricity, we produce power somewhere around 3 cents per kilowatt, depending on the structure. But what we're finding is that most of the people that we're working with, most of the case studies we've done, they're actually more interested in the water than they are the power. Having clean water that they can reuse is a super big thing, and it saves a lot of money. So in short, we're taking sewage, taking the energy out of the sewage and using that to clean up water and to make power. And that's pretty cool. All right. Sorry. I wanted you to see this picture. So using our system, the beaker on the left, the very black stuff, it is not sewage sludge. It's actually much worse and more contaminated. This is water that is left over after they strip the crude oil off of it. But basically, if you can imagine looking in your potty and seeing that before it's flushed, it's a similar kind of grossness, okay? And then after we run it through the system, the beaker on the right shows the water in its clean state. And then we captured all of the stuff that was in the water previously as a sludge, which we then use as fuel. So that happens through our vacuum evaporation system. We're actually going to go out and touch it and show you it. Yeah, show you how it works. So we're going to go out and look at the basic elements of the system. This is a display skid that we've put together that helps you see how it works, what's working, those kind of things. So basically, we have a hydrocarbon catalytic oxidizer. We're going to show you the drive columns with a Pelton drive, the U-charger, the vac evap system. And the vac evap system is really the heart of our ability to use the energy to clean water. It's very, very remarkable. Very remarkable. We're super excited about the results that we have had from that. It just makes the system work. So with that, we're going to go out into the lab.
Okay, we're going to move the computer, so don't get motion sick, please.
Field trip.
Yeah.
Set back up. Making a run for it.
Yeah, get out of here while you can. You guys are all distracted.
He went up those stairs.
Okay, if you don't mind, I'm going to stop sharing the screen and then you guys can and we can better see actually what you're seeing. So only. There we go.
Okay, so I have here, I have a big bucket of super grimy water, but this is some of that grimy water. We're going to put it into the vac-evap system right now. And normally this would happen on a full-scale unit. It would come into some kind of a hopper or tank, and it would be a sewer shredder pump, which would pump it into the system. When we sort of vacuum the second one,
Is this what you saw, Betty?
Kind of like a still.
I'm sick of something. I will.
Who said nothing good came out of Kentucky? Oh,
so we put some water in, and let me explain how this system works. So this tube right here is actually two pipes, one inside of the other. So the inside pipe is where we bring in the sewage sludge or the water that we want to clean. That inside pipe, we fill it about halfway, and then we put it under vacuum. So the vacuum process it lowers the boiling point of the water. So the boiling point of the water comes down to around 100 degrees Fahrenheit. But in that state, it still takes energy to get it to boil. And we bring that energy from the rest of our system in between the outer pipe and that inside pipe. So the steam from the rest of the system then comes and it warms up this inside pipe, but the steam is actually getting cooled. So what happens is, this is the steam coming in from the reactor and the other systems. It's passing into the outside here, and it goes that way, and it is collected off that end. No longer as steam, it condenses and becomes just water. But inside the center pipe, it's boiling at 100 degrees, or even as low as 85 degrees. And it's sucking, as it sucks that temperature down, that steam, we call it cold steam, comes up through this loop. And it comes down through this heat exchanger. The heat exchanger then pulls the heat back out of the cold steam, so it condenses back to water, which then creates more vacuum that keeps the whole system going. So we turn the vacuum pump on at the very beginning, and that starts the process of it boiling. But then once that cold steam passes through the heat exchanger, it drops back to water, and we're able to collect that water in our vacuum tank. And also, we've got a couple of doses here that we just brought. So you can see there's water collected here. It's basically the same effect as the heat exchanger. So we can pull that out to show you. But that's the basic magic piece. Well, one of the magic pieces. And that's how it works. So how do we get the steam and how do we break down the hydrocarbons? That's done in this unit right here, which we call the HCO. So the HCO uses heat and pressure, as Paul mentioned. And inside there, we push the sludge or whatever other biofuel we want to break apart, whatever hydrocarbon chain is available. And then we add additional air. And as we add that air, the hydrogens on the hydrocarbon, so you have a hydrocarbon chain, a bunch of carbons linked together. The H is around the outside. Every time in the HCO, every time a hydrogen has a chance to jump over and join an oxygen, it does, because it likes the oxygen better than the carbon. So what happens is every time an oxygen comes past, we make another water molecule, another water molecule, another water molecule. Pretty soon, we only have the carbon chain left. And that carbon chain, because of the reaction, gets even looser and looser, and we're able to even eat that. And that ends up, every one of those hydrogen jumps and every one of those carbon jumps creates additional heat. So that heat then generates inside of here. And we use that heat to create steam or very high pressure water before it goes to steam. And then we can use that steam to, yeah, you can see. So there's a column here and a column here, which if you think about this column being filled with water, we bring the steam in the top, we expand the steam up here, this column of water gets pushed down and it spins this pelting generator right here. And as it's doing that, the water that was on this side is pushed into this side, and then we change the valves. And so it's basically doing this. You have water up here, you don't have water here, but this side is empty. So the water gets pushed by the steam down here, and then we switch the valves and it comes back up this way. And each time that water is shooting past this pelting set in the pot, which is making electricity. And that is, and you ask, well, why? Why would you do that? Well, the reason is because back in the 80s, when they were developing this type of HCO, they kept having problems with the minerals downstream, fouling turbines or fouling steam engines. In this case, as if minerals collect inside of the piston, there's no piston ring to get clogged by it. It's able to just make electricity. And so that's really cool. It's a very simple device. So, I mean, it's maybe not as brilliant as, anyway, it's cool. It's just cool. All right. So we have another piece, which is also needed. It's needed for the conversion of the waste hot gases that come off of the reactor. In the 1980s, when they were doing these first kinds of units, they wanted to recapture the energy, but as I mentioned, they struggled with that. One of the things that's really difficult about this type of process is getting enough air in to oxidize all these hydrocarbons. But this unit we call a U-charger, and basically, again, it's an air compressor, but instead of having pistons and rings, it uses water. So it also just basically pumps up and down. With every stroke, exhaling the steam travels from here or from here down into the back evaporator. And so basically the heat just cascades down from the hydrocarbons. It cascades back down to producing electricity, producing power, and cleaning water. If you want to produce less power, we can send more heat to more vacuum evaporators. And this is set up so that it's clear and you can understand how it works. But in a commercial unit, there's multiple layers of these vacuum evaporator tubes. There's 3 or 4 banks, and that's how you can process thousands and thousands of gallons at a time. That was the commuter train just passing us. So yeah, the mass transit. Yes, I'm usually on that train, except going the other direction. So that's kind of the high level. There's some additional systems that basically pump the water up to pressure, and obviously valving that manages things. But that's kind of the high level. And so,
Johnny, maybe point out which ones are patented. What components are patented?
Sure. Yeah. So the vacuum evaporator itself has a patent. That's one of the patented pieces. The U-charger and the drive column systems are both also patented. I was surprised that there weren't already patents in that space. It just seems so obvious. I don't know. Yeah, but anyway, we filed patents. We claimed it. We were super excited that it was available. The reactors or the HCOs themselves have a lot of history. We did do some patents on some little tweaks on the inside. We'll have to see if those stand up for several years, but we're part of that body of knowledge. So those are the patent pieces. Questions?
Yeah, I have a
Wade?
question. Yeah. On one of your earlier slides, there was a note about the discharge water temperature being warm to hot. And one of the options was to let that stream flow into waterways. What is the temperature coming out of this? Because I know you can't just dump hot water into the stream.
Yeah, no, that's a very, very excellent question. And in this case, as it leaves the system, it can be down around 80, 85 degrees. But before you would discharge it into the stream, you would probably put it into a tank or a holding pond so it could give up a little bit of additional heat. I think you don't want to put water into the stream until you're under the 70s because it changes the oxygen levels for fish and stuff like that.
Okay. And then for just one of these units, you're talking 200 kW, three-phase power. What generation what would be typical yearly generation capacity for one of these units?
Oh, that's an excellent question. That was on the top of my head 2 or 3 weeks ago. Let's see. So basically, you're running 200 kilowatts times 24 hours a day times 365 days a year. That will give you the kilowatt hours, less your downtime. So yeah, about 1,500,000 kilowatt hours.
Okay. And then what is the capacity of one of these units? Like how many gallons of sludge an hour can it do? And what is that comparative to what our system is processing now?
So, as I recall, in Toledo, your system you're doing, is it 6,000 pounds a day of sludge? I can't remember. You're producing something like that.
That's real close. That's real close to it.
That's real close, he says.
Yeah. Okay. So basically, a 250 kilowatt unit would run all of your sludge. So it would be you could have all of your sludge gone, and you could clean 30,000 gallons a day plus of effluent as well. So I'm not remembering exactly what your number was for gallons, but and if you need more, we can put in a second unit, or it's pretty modular because you just stack these containers next to each other and have that work. So does that make sense? Or did I answer your question? Okay.
Yeah, it seems prudent that if you were going to rely on this, you'd want to have at least two.
Yeah.
So you'd have some redundancy in case you lost one or the flow went up or whatnot.
Oh, the flows will go up.
Yeah.
Right, so one of the things that we deal with here in Toledo, and it's part of the reason why I got hot on this idea of figuring out how to deal with it. So we have had occurrences just since I've lived here where we've had 3 inches of rain in 11 hours. And I don't know about you, but that really overwhelms the sewage system.
Yeah, we wish we could get 3 hours of rain in an hour here in Utah. It happens once every 500 years, and then we're all struggling to swim. But anyway, yes.
You guys hiring? Can I move there?
Yeah, no. So, sorry, go back. I'm sorry, I derailed your question. Go ahead.
Well, the question is, would it be better then for us to actually look at maybe going 2 units so that we can handle when we have the high flows, and then when we don't need it for high flows, use it for other things? In other words, taking in maybe other people's biosolids and running them through the system?
Yeah, absolutely. I mean, another option might be, so here's the one challenge with runoff is a lot of times it's got a lot of minerals in it, but it may not have a lot of BTU value. I mean, if it came off of a field if it came off of a dairy field or a dairy area, plenty of energy. But if it's just rainwater, you may not have a lot of extra.
One of the things we deal with is inflow and infiltration. I don't know if you know what that is in a sewer system.
Right. Yes, you have leaks in your sewer system.
Right. And so that's what blows our numbers way up for what we have to be able to treat is that I&I. And hats off to our public works director. He's made a lot of strides in the last couple of years and we got a lot more to go. But as you well know, DEQ and other government agencies, they don't say, oh, well, you had all that rain, we'll give you a pass. They don't do that.
Right.
And so we need to be able to handle a higher flow than what our average daily is, if that makes sense.
Yeah, absolutely. So there's several options. It still requires some energy to boil that water even in vacuum. So one of the options is that you could reserve some maybe paper trash or other biomaterials, green waste. And then in the times when you have, when you're trying to process as much water as possible, then you would take from those piles, feed them into the system, and then you'd have more clean energy. We also have the option, we can downsize the electrical output and upsize the water processing by adding more vacuum capacity, more vacuum tube capacity. That's another option if you're only interested in the water.
Well, we're interested in the whole thing. It's just being able to, we have to plan for the worst. And so that's kind of what we're looking at. It's plan for the worst and and in the process, get the best available system for us. And that's why we want to work with you on this.
Perfect. When you get overwhelmed, does it go to like a holding pond or does it just flow up everywhere? I mean, how do you?
Go ahead, Bill.
Both. Yes. We have a certain amount of holding tanks that we can divert into until our effluent system catches up and discharges the way it's supposed to and gets caught up. But I mean, we reach limits with that with heavy rainfall and high tides, and the high tides are really a problem because they back up our system because of the gates and things like that. So.
Yeah, you definitely have some interesting engineering challenges. Yeah, definitely interesting. I mean,
Understatement.
Well, and that's part of the reason why we're willing to look at this as far as being a pilot project. Because I'll be honest, if you can solve all the different issues that we've got to deal with, you're going to be miles down the road in getting this to every system. Because you can go to somebody and say, well, we got this problem. Hey, we solved that in Toledo. We're already there.
Yeah, no, I mean, we're excited about looking at it to be sure. And like some of those numbers about the, when you have a high tide situation, when you have a flood situation, I mean, it'd be great to look at what is your storage capacity and how fast could we tackle that? If we brought in, like I said, we still would probably need some fuel of some kind. Maybe GP would be willing to give up some of their black liquor or whatever it is, and that would create the heat necessary to maximize your water production. Or if you have, like I said, green solids or even paper waste, those all would be good ways of keeping your maximum throughput of water high. And then you have to find somewhere to put that electricity. So,
and probably the best way to tackle that is engineering code. I mean, that's something that Johnny and I have done throughout our careers. And you take a problem, you take a look at it, and you know the resources that you have, and then you just start solving it, and you get a solution and you put it together.
Yes, that's true. Oh, we should make a quick note. We're actually doing this presentation from Precision Systems Engineering, which is a consulting engineering firm. And the president wanted me to put up the banner so that you could see it. There you go.
Nicely done. Did you guys have any other questions?
So do you have the visual you showed me of what the inside of the container looks like? Because I'd like Bill to see how easy it is to maintain and to fix things out.
O&M?
Let's do this. Let's just go.
I have seen Paul drive the computer well, so
I couldn't see my cursor.
you might be able to.
There we go. I can see it now.
Yay.
There we go. That's the one. Yeah.
Oh, went away. Hold on. There we go.
Maybe do the one from the top. You can see there's walkways designed. Okay, so if you're looking at this, the unit on the very left, that is the generator system. And in our demonstration, we only showed 2 columns, but we wanted, in reality, there's like 8. And that way it runs like a V8 instead of like a 2-cylinder. So it's much smoother. And then you can see the vacuum evaporators. So the drive column, I'm sorry, the U-charger, the generation system on the left end, you can access through the double doors. So that can come in and out. And then there's walkways between the other systems. So you can get to all the pumps, the valves in this particular layout. We are doing a new revision, which is better, but that's what we have so far. So anyway, that's part of what Betty is talking about is the importance of maintenance ability, and that's definitely high on our list.
And our plan is to train people there. One of your priorities is to create jobs, so we want to participate in that, and be in a position to educate, train, and have them do the support there locally.
And we also have several different components that could be manufactured there in your area. So we think that could be great, and we're committed to do that. As you guys are committed to do this pilot test, we are committed to help in your other goals as well. So that's something we're excited about.
Jackie and Josh, do you guys have any questions?
Well, I don't have a question about the system other than he mentioned black liquor.
Mm-hmm.
Doesn't DP have problems with disposing black liquor?
So currently black liquor at the BP plants, black liquor is a waste stream, and then they usually try to dry it out and then they burn it in their furnaces. So it's not they try to recapture the BTUs that are available in the black liquor, but in the process of drying it out, they lose a lot of energy. So it's kind of a net for them. It's possible, but if we run it through our system, because we don't have to waste the energy drying it out, it's a pretty good BTU source. So that's a possibility. I may have spoken out of turn, but one of our friends manages a paper plant in Texas or Mississippi, and so we were bouncing some ideas about that around. So,
well, I know that in the past we have had accidental intakes of black liquor. Is that gonna like drive the system crazy or top it out or anything?
We would turn it into very clean water and electricity.
Wrong with that?
Josh, do you have anything? Josh?
We put him to sleep. I do that sometimes to Paul.
Yeah,
so
often.
It's not me this time.
We'll talk in the morning, Jackie. So is there any other questions here?
No, we won't. I don't have to work tonight.
Oh, you lucky person.
What's the amount of required downtime per year?
So at this point, we are We are targeting about a 90%, 92% uptime.
Wow.
So that's our engineering target. It may be higher. So the weird thing about this is when you don't have any piston rings and you don't have a lot of stuff that can foul,
You don't have metal on metal.
yeah, you don't have metal on metal in most of the systems. So it ends up potentially being very, very low maintenance. So we anticipate good things.
Still need two.
Yeah. Anything else, Todd? Okay.
Warranty and support.
Okay, Bill, you can speak up. I know you have a voice.
I was just wondering what type of warranties and support you would have for a system like that.
So we are, so our picture at this point is, as we figure out the agreement with Toledo, and we would then, our picture is we would look at your numbers, we'd come up and do some survey, or at least looking at where you want to put it, where the tie-in points would be. We would have Precision Systems Engineering do tie-in drawings. We would complete the basically the engineering study that Paul is talking about. Then after the equipment is done, because this set would be basically a flagship set, we would come up, we would either provide a project manager to local contractors or bring our own, install the equipment, and then we would like to be with you to teach you how to do it over a period of a couple of weeks. But then we would like to monitor the set very carefully for about 2 to 3 months. So probably we would be there with you a lot. And then the way that the computer system is set up right now, we have, through some security protocols, the ability to actually watch what's going on even remotely, and you would have that same access. So you'd be able to see what was happening. We'd be able to track data. Then we'd like to come back in about 3 months and take apart a few key pieces and just confirm that everything is the way it should be and that we called all the materials correctly. So if for this particular set, I would anticipate a lot of interaction with us. In the future, other cities may not want to do that. They just want to plug and play, and that's great. But we would like to be very involved with you too.
And then once it's commissioned, as far as a warranty?
Yeah, once it's commissioned, as far as a warranty.
Probably a typical warranty for heavy industrial equipment.
Yeah, probably. I mean, we would look at the T's and C's and figure out what makes the most sense. But that would be part of the negotiation of the contract, and we would want to make sure that we're fair and providing good pieces for you. So we have done a lot of equipment over the years in plants, not just ourselves manufacturing, but putting equipment into plants from other vendors and other suppliers. And we want to make sure that you have a great experience, because we want to make sure that you talk to everybody up and down the road.
Question, so this being a pilot project, what are the costs associated to the city of Toledo?
Betty?
Okay, so.
But I don't want to factor in any kind of federal grants.
Well,
No,
that's,
this is all based
they're
on
who's grabbing
money.
a hold of this.
Okay.
where the plan is here tonight. I get consensus from the council to continue to work on this project and move forward, find the funding and work towards EPA approval of the way the system is run. And I've already mentioned it to Senator Merkley that we would be asking for money. We're asking for $6 million because we also want to build a training facility and a place to assemble and or train technicians and whatever we want to do here in Toledo. So But I want it all to come from the feds.
Right. Well, the reason I phrased the question the way I did was because if Toledo has an invoice, doesn't matter who's paying that invoice. If Toledo has an invoice, the project may be eligible for energy efficiency and conservation funds from BPA. Which means even if somebody else is paying the bill, if Toledo has an invoice, they're eligible for a rebate up to 70% of the project cost based upon energy savings.
Nice.
Oh.
Okay, so, but I think our plan, our plan for next week is to talk with,
Can we get an invoice?
talk
Yeah,
about it, how we're gonna set up.
That's provided that the serving utility has those funds to pass through from BPA, which I have control of.
So depending upon what you say tonight, my avenue has been through Representative Schrader. And I'll be talking to him at his town hall next week about it if we have consensus tonight. They're very, they're very excited about this because it's a game changer for every community in the entire United States, not just Toledo. And they understand that Schrader's aides especially understands that the issue is EPA and getting them to sign off on all of this. And so that's what they've said, that they would be very, very willing to take point on. So waiting to hear, that's why we're doing this two-pronged. She's going to be talking with Senator Merkley. I'm going to be with Representative Schrader and try to get this driven through. I did not know about that little joyful piece of dollars.
It is shocking how many of our cities don't know that we have money.
Yeah, that's pretty nice.
Yeah.
I look at it as it checks off all the boxes. It's environmental, it's jobs, it's, global warming, it's everything that they're looking for. It's infrastructure.
And it generates power.
And it generates power, yeah. So I, as far as I'm concerned, the federal government should say yes to it because it checks all their boxes that they're all about right now. So, and, so it's very good for us in a lot of ways.
How many jobs are we talking about? How many jobs are you talking about?
Well, initially, this is just my guess, okay? See, here's the crux, okay? The manufacturing place to do this is the Stedco site, okay? Without a doubt. It's got rail access, it's got, it's fully serviced. It is, quote, shovel ready according to the state, okay? So part of my job is getting the tribe to come on board with this. They were interested, but they've gone through a complete change of hierarchy over there. And thank God I still know my tribal council members because they're still interested. But them being wise say, well, you got to take it up with so-and-so and so-and-so because they're our managers. Well, that has changed 4 times in the last 18 months. So I'm hoping for some stability because I think they would latch onto this in a heartbeat because of what it would do for the Silettes and for the tribe itself. And so this thing could be as small or as big as anything you can think of in this area.
Yeah, well, Peter Lahanye is interested in teaching his students. I'm sure Oregon Coast Community College is gonna be interested, if they can get classes from it. But, so that's how it's gonna get jobs, is by these people learning it and then taking themselves out into the world to teach other people and to build them and
because part of what they talked about is actually doing some of the production of this process here.
Right.
So that's why that's why I'm working on the tribe. If I can just get somebody in the office for more than 4 months, I might be able to get somewhere down the road with this, so.
Yeah, and we would be very interested in both help set up some curriculum for technicians. Some of it is very basic, how to read a voltmeter, check these pins. But on the manufacturing side, there are some manufacturing skills that would be great for your people there, from putting together stainless steel tubing to even some stainless welding. So there's pieces that could be done. We also do some quirky little ceramic parts, and those are things that could be done. So Paul's mission is he is envisioning and setting up the manufacturing plants and the manufacturing facility. And so depending on how much you guys want, we could give you actually a layout for a specific module or a couple of modules, or it depends on how big this gets, but it's possible that at some point you would have a full size, if you wanted to, and you could support it, a full size manufacturing or assembly facility there, because the potential, I think there's like 16,000 sewer treatment plants that are run by cities around the US alone. So the amount of work that could be done it's staggering. And we can do a good chunk here in Salt Lake, but there'll have to be some other sites set up. And why not you guys, if you want it, right? If you want it, so that's there's just a lot of potential here. It's a really interesting model. So.
Anything else, Bill?
No.
Okay. Anybody?
What's the plan if this doesn't live up to its potential, or doesn't scale, or just completely fails? What's the plan then?
The plan for what?
We'll have this facility.
Okay.
So it's all about engineering and incremental improvement. If you look at the automobiles that you drive, they are significantly more complicated than this system. But when Henry Ford built the first Model T, it was kind of the same level of technology, right? So it has to start somewhere, and then it has to continue to grow incrementally, get incremental improvements. And I don't know, we've done so many projects where, when you turn the switch the first time, it maybe doesn't do exactly what it's supposed to, but you just keep working on it, you modify it, you make the adjustments. Most of the time, it just has to do with programming and valve timing. That seems to be a big deal. But in this case, it's really pretty basic physics. And we anticipate that it will, we've already done engineering for a 200 kilowatt, and the mass energy balances are all complete. We've looked at it. It's, so yes, it's a little bit bigger than this, but it all is the same stuff. It all makes sense. That's why we built this one the way we did, so we could prove that one. So we're pretty confident. How's that? It's going to go.
I'm glad you're confident.
Mm-hmm.
But as I said earlier, I plan for the worst, right? So Todd, this is why this system intrigues me so much. Did you hear about what size container it fits into?
Yeah.
Guess what? That can sit right up above our current wastewater treatment system without disturbing our current wastewater treatment system. So the backup is always there and available. Right?
Yeah.
Until we get all the kinks worked out of this thing and it's running perfectly, right? Then we can switch over to full-time use of it. But we have the backup. I mean, to me, that was when they said it fit in a container that size, my brain went ding, we have the place for it right next to it. It would require minimal plumbing, minimal work to get it operational and to have the backup while it's the test facility, because we are literally talking about being the cutting edge. Well, whenever you do cutting edge work, you don't want to do it without a wire. Well, we have a wire, our system is still there. So I hope, does that answer your question? Okay. Chief, you had
just a quick question. I'm sure it's already being taken, into account, but you're producing electricity and you got steam pressure and then energy. What about an overrun or an overpressure levee system because it's steam? Fire rescue response is what I'm looking at with that. What type of shutoffs, exterior?
So in the top of the shipping container, we have, and this could be positioned in different places depending on your location or what, what you're up against. But in the top of the container, we have PSVs set up so that if there is an overpressure situation, there's a way to relieve that. The valves themselves and the logic in the system all are fail-safe open or fail-safe close, depending on what they need to do. Even on this system right here, we used fail-safe open or fail-safe close, depending on how we wanted to control it, or if the power went out, what we wanted the response to be. So yes, in the case of and you can operate it, as we mentioned, remotely from other locations if you have the security and password to get in. But we could do something as simple as put a switch on the outside, which is the emergency stop button. And if there's a fire in the area or something happens, that switch would then initiate the shutdown process and the cool down process. So there's not, at any given time, there's not a ton of steam, but there is, and it becomes lower pressure pretty quickly as we start driving stuff. But it's, safety is very important, and we're very much on board with making sure that your people are safe and that there's not an issue there. It's important to us.
Yeah, maybe this would help a little bit. So the background for both Johnny and I, we've spent years and years and years in plants and facilities, both as engineers, as operators. I worked in maintenance at a plant for 4 years as in supervision, and safety is a top priority. Some of the facilities that we go into as engineers require safety. They demand safety, and so it's second nature for us. It's part of what we think about. It's part of how we plan things, and that goes for maintenance as well. Maintainability is vital, and engineers get a bad name by those people that operate and maintain equipment because you can't access the bolts, you can't access the door, you can't. I've lived that personally, and so that is high on our list, and it's part of our execution plan to make sure that all of that is as well taken care of as possible.
I'm still a little sore over my Colt Vista. I couldn't get my hand in where I had to tighten the belt on the alternator. And it was because a Japanese guy must have designed it. There's just no way for me. Nothing against it. Yeah, anyway, but it was a great car. So.
Anything else?
Yeah, what's the longest run time you guys have on one of your guys' machines?
What's your longest run time so far?
That's a great question. So we have run times on components. We're still working on length of time. So
how long have you the back-to-back? How long have you run that for?
So we've been running the back-to-back for, well, let's see, before last fall was when we started, right? We were doing back-to-back stuff in December, so it's been,
and you
9
run
months.
Hours at a time.
Yeah.
So it doesn't sound like a lot. So our demonstration model is not necessarily set up to be material in, material out. It's proof of concept to show that the different components work in concert with each other. So we don't have a long run time, but we have run time on every single piece of equipment, and we are getting to where we want to be.
Right. We have learned a lot from this unit. We've learned lots and lots. And
so in case you're wondering, Todd is our resident guy who has to try and stick his hand in that Vista section to try and tighten that bolt. So these are the kind of questions we get from Todd. And he always makes us go, oh yeah, dang.
I think we should get together and brainstorm, because that's great.
That it's designed for that, at least.
Have they done any work or made any contact with Kennecott?
Say that again?
Have you made any contact or done any work or plan to with Kennecott, the mining company out there?
So personally, I've worked out there myself for the engineering firm that we are at right now. Johnny and I have both done projects out there. We haven't talked to them about this because we're still trying to get to the point where we have a full working model before we would approach some larger companies like that. But where we really see the greatest value is in making water and in cleaning water and taking care of cities and problems similar to what you have. So that's really where we're looking first and foremost before we approach companies like Kennecott. But absolutely, they're on the list. And if we could talk about the different industries that we could serve, again, if there's a BTU value it's in that water, we can serve them.
We did a case study for a milk processing plant here in Salt Lake, and I was amazed at how much water they get through every day, and their cost for treating that water was it blew my mind. They were getting a payback in like a year just on the sewer cost, the sewer processing costs that they were paying. So it was pretty interesting. But there's just so many. There's food plants, and there's the sewer treatment waste plants. And there's the idea of actually like using one of maybe a smaller version to do processing of dairy waste. Like I don't know if you've ever lived near or downstream from a dairy, but it's phenomenal. And so
not in a good way.
Yeah.
Yeah, I was gonna say phenomenal. That's not the word. Derriere.
Right.
So it's an opportunity for sure. In the mining application, like, yes, they probably have water that they want to process, but what do you use for the BTU value to do it? It's like, that's the question. So you have to find a balance there where you've got some BTU and you've got water that you want to clean up. So.
Yeah.
Anything else? Jackie or Josh?
I just had a little bit of a question. I had to take a work call a few minutes ago. I apologize if this has been gone over. But you talk about the water that comes out of it being purified down to like 116 parts per million, and that it meets World Health Organization standards for clean drinking water. And I was just curious what those standards were versus what we have to treat our water to.
Josh, the train just went past, we missed your question, but you were asking about what is the quality level that you need to meet the World Health Organization, or can you restate the question?
Yeah, in your slideshow, I saw something that said that this water could be cleaned down to like 116 parts per million and that it met World Health Organization standards for clean drinking water. So I was curious what those standards are in comparison to what like a municipality would need to meet for clean drinking water. So like, is this water totally ready to drink when it comes out of here, or would there still be processing that would need to be done on it?
So, so ideally, yeah, at 116 parts per million, and then it would meet World Health Organization. Well, typical drinking water falls in the range of between 300 parts per million and 600 parts per million. So that's kind of the parts per million range. The other thing that we look at is, so, and I don't know where Toledo is, but it probably falls in that range somewhere. I mean, the other thing that you want to look at is, are there other things in the water that, maybe very small quantities, but for instance, mercury. You don't want mercury in your drinking water, even if it's only 116 parts per million. You don't want, certain microplastics, or I forget what it is now, but it's a polyfluoroplastic that's used a lot in like firefighting, and it's starting to show up in water aquifers. And originally it was thought totally non-toxic, but now people are starting to realize that, hey, it's accumulating in the liver. Your body can't get rid of it, and now it's starting to plug stuff up. So the the EPA and others are starting to recommend that, hey, that particular plastic shouldn't be in your drinking water down to certain low levels. So the long answer to your question, I'm sorry, was just, yeah, we're at 116, 300 to 600 is the typical target.
It's considered good, but you can actually go to 1200 according to the rule.
Yeah, it's World 12. Yeah, that's right. So, that's kind of the range. And then you step back one more layer and you say, well, what is left in it? And what we're seeing and what we're finding is that very, very low traces of anything bad. And ideally, the plastic type of things like that PTFE molecule and other things also get taken care of. They also get removed into the sludge. So I don't know, did that answer the question? I feel like I was going around in circles. Sorry about that.
Yeah, no, that I think answers it. I'm just trying to understand if the water coming out of this, was drinkable, or if it needs to be processed to actually be like municipality quality drinkable water.
So the test results that we've gotten back says that except for, I think it was odor and turbidity, it qualifies as drinking water. So we've made some adjustments to our vac-evap system. We haven't rerun those tests. We also want to get everything working in concert first before we take those tests again. But with at least understanding how it works, we feel like that we have been, or that we should be able to eliminate those. And then really, we can tell you everything that this little unit can do, but we want to scale it up and get those tests, because then we can be definitive.
Thank you. So I think we're kind of just not at the point where you guys have had long enough to test it fully to get it to that high quality.
So initially in the first pass, we were drawing, we were taking all of the vapor that came off of the vac-evap, and we were putting into the same collection. We realized, of course, that a lot of this nasty stuff has nasty odors that are actually little molecules and other things like that. So what we've built into this unit is we have the first stage is we take the vapors that come off before we distill the water, and we send those back to the reactor. So that includes, any weird stuff. And then we don't start collecting the water until after we've reached the stable temperature and we've got the right, we're just basically getting this distillation off the top of the water. So, and that's pretty easy to see because of the temperatures, and you can program for that pretty readily. So we have already built that into this test unit, and we are doing tests with it. So we're confident we'll be you can go straight to drinking water, and you don't have to do RO first. Now, that having been said, there is the idea that, hey, if you're running sewage water in, it's EPA is like, you can't then clean up and drink that. So it may be that you discharge that to a pond or someplace else, and then you can bring it back in. Basically, at some point in the future, we would anticipate that people will realize, hey, this water is cleaner than the water that comes out of the tap regularly. Let's use that instead. At this point, there's a regulatory issue that would have to be worked on before that could happen. And there's also the psychological hurdle of that is definitely a challenge. So, however, if you think about it, the city upstream is dumping their effluent in, and then the next city downstream is sucking it back in and drinking it. So we feel like it
all goes downhill. Yeah.
Better option.
But Josh, I think the net of it is every water district is going to have their own set of requirements. And so when that city goes online, obviously beforehand, before it's commissioned, we have to address anything that they require in order for it to be safe for drinking water. But right now, it's ready for use for ag, for sure.
Okay, thank you. I appreciate it. I was curious because I know going forward as we discuss water shortages and droughts and things like that, you know, all the water that's here is the same water that's been here for hundreds of millions and billions of years. It just changes, you know, a little bit of the makeup of what's in it. So, you know, I definitely agree that there's the psychological factor of, ew, we're drinking that water. But, you know, that's a direction I think we can go once we get people over that hump. So thank you for your time.
Yeah, absolutely.
Thank you to all. Betty, Rob, thank you.
Hey, there's one issue.
Introduce
We've
yourself, Ricky.
got to remember that
Ricky,
it's
introduce
Ricky.
yourself.
It's Ricky Dyson.
Thank you.
Hey, we've got to remember that for years and years and years, we've had an international space station. Guess where they get their water?
Right. Uh-huh.
They're not shipping tanks of water up there.
No.
We know where that comes from. And we accept that perfectly well. We don't have a problem with that.
Well, it's always good for somebody else is how that psychology works.
Somebody else's.
Right, Toasty?
Absolutely.
We can just sell it as astronaut water. People will love it.
Hey, there you go.
Bottle it.
Boy, talk about coming around again. Right. So any other questions for these gentlemen?
Yes, I got another one.
All right, Tom.
So say the machine's running, we get our excessive INI in, and then we have to add more fuel to it to effectively, you know, take care of it. Does the machine have to go down to reintroduce more fuel, to take care of the INI coming in?
No. We just, yeah. It has a controller kind of like the throttle on your car. It basically watching the oxygen and the anything coming off the exhaust, and it's adjusting the mixture going in based on that. It's almost, it's a very similar engine controller. So if you need more power, then you step on the gas. If it senses that the electrical load is higher, it can ramp up to that to its full capacity. If you want to run more water, we'll just set up a protocol where basically you put the pedal to the metal and things just going to run full out as long as you keep giving it fuel. So if you run out of gas, it will slow down. It will not. I mean, if you run out of the fuel, it's like a car. It's gonna start slowing down. You'll have a few hiccups, but that's.
Well, as I understand it, though, from what he's saying, we could introduce it into the fuel line before it ever got to the unit. In other words, if we know we're about to have one of those great wondrous events, we could then enter into the fuel system something to make up that fuel shortage.
Right, and in reality, we're kind of like the GM Flex vehicles. We can take multiple forms of fuel, and we have different ports that go into our HCO. So we could run on 1, 2, or 3 different fuels at the same time. The system doesn't care because it's doing the same thing to every single fuel, and it's looking at it from an elemental level, and it's just looking at hydrogens and carbons and oxygens, and it's just doing its thing, stripping away. It doesn't care what type of fuel it is. So yeah, we could be ready to turn on more fuel, a different fuel, 2 fuels, 3 fuels.
Oh, and the other thing they told me when we were there, told Dan and I, is that if it's turned off for any reason, it takes a couple of hours to restart, not days, weeks, whatever it takes. Large plants, it takes a couple of hours to get hot again to the point where it can go back. Yeah.
Lost you there for a second, Paul.
Oh, wrong. That was Johnny. Johnny didn't hear what you said.
You said something?
Oh, we just said, oh, I don't know, what did we say? I don't know. Did I say something?
It was horrible. I'm trying
If you
to.
said it to Betty, she'll remember it forever. I'm just telling you. She's better than a tape recorder. All right, if there's no other questions. All right, gentlemen, thank you very much.
You're so
Thank you.
welcome. It was fun.
And we'll let you know what we decide. I think I'm going to add this as a discussion item for consensus. Now that we've had this. So when we get to discussion items, we'll talk about it amongst ourselves. Does that work for everyone? Sure. All right. Thanks, guys.
Yeah, all right, have a great evening.
You too.
Bye.